All right, so why don't we begin? All right, so today's the fourth lecture in this section of, oh man, I'm so used to teaching 374 in 2 sections, I have that whole thing memorized. And today is the fourth lecture in 364 in our course, and today we're going to be talking about linear algebra, but just not linear algebra, a whole bunch more. I'll change it later. A whole bunch more, including more matrix operations, solving systems of linear equations, and I actually got rid of eigendecomposition. We're going to be basically introduction to matrix algebra, introduction to matrix calculus. Okay. All right. So those are the big three we want to get through. Once we get through these things, we'll have enough background knowledge to start on auto differentiation next week, which is the big machine learning course, right? So let's start off with an easy one. Last time we talked about matrix operations. Well, we ended on matrix operations, simple matrix operations, matrix multiplication, stuff like that. So let's kind of finish that off, and let's just go a little deeper into slicing, which we did last week, but we're just going to refresh our memory and talk about some more tensor slice operations and touch a bit on broadcasting. So let's imagine we have a particular tensor. Again, as we know, a way to define a tensor of some predetermined values is just to say torch tensor and write out the actual array. So supposing we have the tensor, what is the shape of this tensor? Let's just get our minds flowing real quick. What's the actual shape of this tensor? Yeah. 228. Oh, perfect. Yeah. So 228, because from left to right, you have two matrices here. Well, let's just look at it from right to left. The last dimension is 8. The second to last dimension is 2. And the third to last dimension is 2 also. Okay? That's good. I'm glad you guys are doing that. I don't know why, but for some reason my mind always defaults to looking at these two and like having them to be the first 2 dimensions. So always my instinct is to say that the dimensions are 2, 8, something, 2, 8, 2. But that's good. It doesn't confuse you. Excellent. Okay, so 2, 2, 8. Oh, not there. Ha, that would be funny. I forgot to run that again. Yep, there we go. 2, 2, 8. Okay, so some fun slicing. So let's go over some slicing problems. We are again have the same matrix, same tensor, 2, 2, 8 tensor. How would we slice this? How would we slice this tensor up in order to display every other value in this first row? So we will want to have, if we want to slice this up in a way that basically we take basically we're ended up with a tensor that is 1, 3, 5, and 7. Okay, every other value in the first row. Any ideas? We would have to, I'm going to, no. There we go. So remembering what we did with matrix slicing, we need to slice up each dimension in some way. How should we do it? Yeah, please. Good. Excellent. Okay. What should the last one be? colon 8. Oh, let's see. So colon 2, would that work? Yeah, that works. What was the other option? Colon 8, colon 2. I think that works also. Oops. Yeah, that works also. Yeah, perfect. Yeah, so what's the shape of this tensor? How many dimensions does this tensor have? Let me phrase it that way. How many dimensions does this tensor have? Huh? Say? Yeah, the new one. Yeah, the slice. Sorry. I promise, sound sure. Yeah, please go.
It's 3, right?
Yeah, it's 3. Yeah, exactly. Here, I'll in fact, I'll prove it to you. Print a dot. Oh, sure. Yeah. Oh, not A. Oh, then I have to. Okay, hold on a sec. B equals. Yeah, there we go. Okay, good. All right. Yeah, that's the same thing. Let's see. Oops. Oh, what will the code be? Let's look at the inverse problem. I sliced up the tensor in some manner. What's the code below going to display? Yeah, please.
It'll display every third element in the first 2 rows in that first section.
It'll display every third element of those first.
Third. It's only 1 colon.
Okay.
Up until the third element.
Up until the third element, good. For what? For which values? So which values? Just say it out loud.
It'd be 1, 2, 3, 10, 11, 12.
Yeah, I think that's reasonable. Let's see. Yeah. All right, good. You have the same tensor. What will this code below display? What will the code below display? Please, yeah. The second row in each copy. Okay. The second row, so what numbers, basically? 10 through 17, 81 through 88. Okay, 10 through 17, 81 through 88. How many dimensions will this have before I hit enter? Yeah. Please, yeah. 3? All right, let's see. Does this have 3 dimensions? Let's say print. Oh, I got to do B equals. Only has 2 dimensions. Why? Yeah, please. Oh, that's an interesting argument. Oh, I don't know how the software. So the comment for everyone in recording land is that it doesn't count as a slice if you only pass in a scalar instead of a vector. I don't know the answer to that. I mean, this seems this like enters like this sort of goes from sort of technical definitions to almost a philosophical argument. But I will say that the spirit of the answer, I agree with you. Basically, if you pass in a scalar for one of the dimensions, you're not really slicing the vector. Well, you are. You're taking a portion of that dimension. I would still count it as a slice. But I think the bigger thing is that when you pass it in a scalar, you're basically eliminating that dimension, right? You're basically saying that you're compressing that dimension into nothing. So a dimension, a dimension sort of represents a range of values. So when you pass in a scalar, you don't need to represent a range of values. You only represent a single value in that dimension. So in that case, what the program does is that you basically eliminate that particular dimension, and that's why you compress it. So one of the things, just working our way back to one of your earlier examples over here, if we wanted to actually, for instance, we had these 4 values, and you didn't want it as a 3-dimensional vector, one of the things, as a 3D tensor, sorry, one of the things to do is sort of eliminate the semicolons, and that would eliminate the extraneous dimensions. Does that make sense? So every time you slice with an array, let's phrase the rule like this: every time you slice with an array, the dimension is preserved. You still have the dimension, even if the array is 1 element long. But when you slice with a scalar, you sort of eliminate that dimension, and everything compresses that. Make sense? I thought that was kind of neat. It's the type of stupid interview questions interviewers love asking, right? So now you know. Okay. So everyone's familiar with slicing. That's good. So slicing's counterpart in Python is broadcasting. Show of hands. How many of you have dealt with broadcasting before? You know what broadcasting is? Okay, good. Good. Then I'm glad I'm going over it, because to be perfectly honest, I had no idea what broadcasting was. It's not a classic operation until I was doing something in Python and I couldn't understand the behavior. So let's go over broadcasting. So quick diversion. I create 2 tensors. My apologies. And one is a 2 by 1 tensor, 2 rows by 1. And another is a 1 by 2 tensor. And in fact, instead of doing this before, I don't want to spoil the question, but I will print A, print B. Okay, makes sense, right? They both have 2 dimensions. One is along the x-axis, one is along the 0 dimension, and the other has 2 values along the y-axis, along the 1 dimension, right? So the question is, what will the sum of these 2 tensors be? Please, yeah. It'll throw an error. That is a good intuition. Let's see. No error. And in fact, something kind of unusual, right? It doesn't throw an error, and in fact, you get sort of a pseudo Hadamard product of the 2, right? So the question is this a torch behavior? Nope. This is an NumPy behavior. So NumPy. So since torch basically derives its existence from NumPy, we could analyze NumPy arrays and torch arrays in this case, and so broadcasting is an element of NumPy. So the question is, what's going on? What's going on? And so, while everyone's familiar with NumPy and torch slicing, NumPy also known as torch slicing, broadcasting is less used, but it does come up in machine learning, and especially, what's going on? Oh, I got a really weird voice feedback thing going. Okay, so especially since sort of dealing with large matrices, adding them together, adding, multiplying them, all of that, it's useful to go over it because because you'll see in a moment why. Let's go. So when we add an array to a scalar, we know we want to add that scalar to every single element in the array, right? But another way to look at it, so code-wise, we have an array. It has a couple values in it. We say b equals that array plus a scalar. We add that scalar to every single value, right? Okay, so the way we think of it the way I think of it at least, is that simply, the Python sort of figures that +1. You're just, that +1, it sort of, it figures out what you mean. It figures out that you want to add +1 to each element of the vector, right? But really, if we think of the sense that a scalar is simply a one-dimensional value, and a vector is a one-dimensional value, and a scalar is a zero-dimensional value, then this should throw an error too, right? Because if we're arguing that two incompatible matrices should throw an error, two matrices of different dimensions should throw an error, then this is basically two matrices of different dimensions, and they should throw an error, right? But also, the thinking is we don't want it to, right? We don't, even though it's not technically correct, even though if this wouldn't be technically correct in a math textbook, we don't want this to throw a value. So what's an alternate way to think about this? Well, in Python, what's going on? Okay. In Python, another way to look at this is that b, that scalar, not the dimension of b, the dimension of the scalar is being stretched. So you start off with a vector, and then you're adding a scalar. But Python is looking at that scalar and saying, I want to add that scalar to each element. I want to add these two things, but they're not the same dimension. So maybe I could force it to be the same dimension. Maybe I could stretch the scalar so that the dimensions of the two beings match, and then I could add them the way I would add any other two vectors, right? So this is what's known as broadcasting. This is what's known as broadcasting. Simply the idea that you have one operand, you have two operands that don't necessarily have the same dimensions, but some of their dimensions are the same. In this case, they have the same x dimension, right? Both cases, the dimension along x is just a single value. So what could you do in this case? Well, you could stretch the other dimension and make the two match, and then you'd be able to add like normal. Okay? It works with matrix and matrix operations too. So for instance, I defined a matrix that was 4 rows by 3 columns right here. And then I defined another matrix that was only 3 columns, right there. Right? And so what happens in this case? We have this matrix. Can I zoom in? Yes, I can. So I have this matrix. And then I have the second operand that doesn't have the same dimensions. But we know the dimension along y is the same for both, right? So if we simply stretch the x dimension for the second operand, we could get two matrices that have the same dimensions, and then we multiply them in this case as normal. Make sense? So again, this is known as broadcasting. All broadcasting means is that you're stretching one or more dimensions in usually you're only stretching one dimension in a operand so that you make two operands match dimensions so that you can perform an operation. Okay? And so, is this technically a part of math? Is this in the Principia Mathematica? No, I'm pretty sure Gödel never defined the rules of broadcasting. But this is very useful for a variety of machine learning tasks. Okay? So, the general broadcasting rule is that, and NumPy or tensor or torch, sorry. NumPy or torch, as we're going to commonly use, compares the shape of two arrays, element-wise, from right to left, and tries to find two dimensions that are either equal, or one of them is size 1, right? So the dimension that is of size 1, and then the other operand has a dimension of size n, it will then stretch that dimension so that the arrays match. And that the other major thing is that the two arrays don't need to have the same number of dimensions. In broadcasting, you'll add a dimension. You could add an extra dimension to make the number of dimensions the same. You could basically instead of an array instead of a one-dimensional array, you could have a two-dimensional array that simply has all the values along x and just an extra dimension along y. But the resulting array will have the same number of dimensions equal to the input array with the largest number of dimensions. So, knowing that, kind of knowing the general rules of broadcasting, what does this code snippet produce? What do you guys think? Any intuition behind this code snippet? What do you think? Okay. Should it produce anything? Yeah, please.
I guess I don't know exactly what it is, but my intuition would be another 2 would first be copied to that first row. So where the 3 is, it went with another 2 because that would copy over, and then it would copy over that whole row.
Yes, that would be my intuition too. Unfortunately, our intuitions are wrong. If we actually do this, we actually get a runtime error. So why do we get a runtime error? It's because none of the dimensions match in this case, and none of the dimension. There is one dimension along x that's a 1, so we could stretch this. We could stretch the 0 dimension here. We could stretch it and to make it 2, but then this dimension 3 doesn't match this dimension 4. Okay, so this is a nuance here, and this is why I'm not a huge fan of broadcasting. It's because it almost seems like magic, and it's very easy to fall into a trap where the computer, where Python interprets it, or Python does something you don't intend it to, right? So you have to be very, very careful. But it is useful in a sense to produce tensors that would be fairly difficult to define normally. So for instance, let's say I wanted to make this bigger. Let's say I wanted to define a tensor, a 4-dimensional tensor, where each value, each element in the tensor corresponds to the value where each dimension corresponds to a particular digit, right? And the value of each element corresponds to the number A, B, C, D, okay? Where A, B, C, D are digits of a number. So normally, how would we do this? We could do this using a for loop. We would have to define a torch array we could just define a torch array of zeros. Torch array of zeros, do a for loop and change the value of each element. That's okay. But we could do something much more pretty, which is simply define we would define a tensor of 10 values along each dimension. And then we multiply, for instance, the A tensor by 1,000 to denote that this A corresponds to the fourth digit in the number. Yeah, the fourth digit in the number. And then we just add them all together. So what's it doing? Basically, the program is going through, and in this case here, when it's trying to add A and B together, it's saying, okay, A is a 10 by 1 by 1 by 1 tensor, and B is a 1 by 10 by 1 by 1 tensor. So if we add those two together, we're going to get a 10 by 10 by 1 by 1 tensor. In fact, let's do that. Print A plus B. Let's just do shape. I'm going to do x dot shape. Okay? So when we add a plus b, that's going to stretch both a and b. It's going to stretch a along the second dimension, along dimension 1, and it's going to stretch b along dimension. It's going to stretch a along dimension 1, yep, and it's going to stretch b along dimension 0, resulting in a 10 by 10 by 1 by 1 tensor. And then we're going to add x plus c, parents, x plus, parents y. Shape. We're going to add that together. So again, x was stretched along the second, along dimension 2, and c was stretched along dimensions 0 and 1. And then we add them all together. We add d to get a actual x tensor, to get an actual, let's call it z. To get z, oh, what did I do? Oh, that's supposed to be, there we go. To get basically a 4D tensor that has for a 4D tensor where every element is equal to a, b, c, d, where a, b, c, d are the digits and the actual numerical value. Does that make sense? Okay, good. Good. So, interesting little bit of Python trivia there. Yeah, apparently this comes up in interviews. God, I don't know what I'd do if I have to, well, I mean, interviewing in this day and age, man. Sucks. All right, so, okay, everyone good with broadcasting? That's the basic idea. We're not going to do it too heavily, but the most important thing is to make sure you do realize it is there, because A, it could be useful for you. It could be useful for you if you're careful, but also B, if you're not careful, it could do, like you could mistakenly add two matrices which you thought were the same shape, but they're not the same shape. But Python was like, wait, I could make this work. And then you go down, and it keeps going, and then you finally hit an error somewhere way down in the code, and you don't understand why all your tensor shapes are messed up. This is why, okay? So Python, one of the beauties of Python is it'll try to help you, try to interpret what you do, what you mean, but also one of the terrible things about Python is it'll try to interpret what you mean, which, depends on how much you trust computers or not. Okay, so, now that we're done with broadcasting, let's go on to systems of linear equations for obvious reasons, right? Linear equations are pretty much everywhere in machine learning, so it's a good thing to be able to solve systems of linear equations, because that will become very relevant when we do backpropagation, to train a system, right? So, what is a linear equation? Is a collection of a system of linear equations is a collection of two or more linear equations involving the same set of variables, right? So we have n variables, and we have n variables, and then we have a bunch of coefficients to each of those variables, and they add up to be sum b. Okay, so this is the general form of a linear system. But so how do we solve for this? Well, we could do the grade school method, right? We could simply try to solve for it directly by combining different, by adding different equations together to eliminate one or more coefficients, and do that iteratively until we're left with x of something is equal to something, and then we solve backwards, right? That's what we do. That's how when we first learned of linear equations, that was how I'm sure all of us learned how to solve them, and that works great if there are only like three or four variables. If there are 1,000 variables, that won't be great. That won't be great to sit there and try to figure out, right? So what do we do in this case? Well, we have to figure out, we have to find some alternate notation. So one way to simplify the notation is simply to combine all of these coefficients and just simply say this vector times x1, this vector times x1 plus this, all the coefficients plus x2 plus all the coefficients is equal to this possible vector, right? That makes sense. A vector equation. Linear combination. We'll take the vector equation a step further. Knowing our matrix multiplication rules, we could take that vector equation a step further and simply say this system of linear equations is representable by a coefficient matrix, A, times the vector that represents all the variables, and that these two together would be equal to B. Okay. So, I'm sure you guys have seen this before. So doing things this way, defining things this way allows us to write in a very compact form. The system of linear equation is simply ax plus b, where a represents all the possible coefficients, and b is the results, the sum of all the of each linear equation. So writing things this way allows us to solve for x by simply taking the inverse of a and multiplying it by b. We know all the values of a. We know all the values of b. So as long as a is invertible, then we can multiply it by b and get a solution for all the variables 0 through xn minus 1, or x1 through xn. Make sense? So we could do this by hand. Let's start off with an example. We have this following system of linear equations here. 2x1 plus x2 plus x3 is equal to 4. x1 is plus 3x2 plus 2x3 is equal to 5, and x1 is equal to 6. This is not actually kind of nice because this actually takes care of one of the variables right off the bat. So we could definitely solve this by hand, but for the sake of argument, let's just do things the matrix way and simply define the coefficient matrix A. Simply it's each of these coefficients here. 2, and this is the coefficient, the first row is the coefficients of the first linear equation. So we got the coefficient of x1 is 2, the coefficient of x2 is 1, the coefficient of x3 is 1, and all of this is equal to 4. And so we do the same thing for the others. If there is no x2 or x3, the coefficient becomes 0, of course. So we define the coefficient matrix, and we define the solution, the sum, the n sum vector. And then we solve for x by simply taking the inverse of this matrix and multiplying it by b. So the inverse of this matrix, if you find the one thing is you got to know how to find the inverse of this matrix, which I'm sure all of you know how to do from 257. So find the inverse of A, which is this value, right? This matrix right here, 0, 0, 0, negative 2, 1, 3, 3, negative 1, 5. And then you multiply it by B, this matrix. So you multiply by b, so you get the following solution. Actually, I think I made an error here. Did I make an error here? Because this will be 0, right? Say that again?
The first line of the matrix should be 0, 0, 1 instead.
Yeah, I think it should be 0, 0, 1. Let me check. Yep, it should be 0, 0, 1. Oh, sorry. Well, can I fix this? Yes, I can. Yeah, that was weird. I'm surprised because I remember checking it against the code last night. I was like, oh, everything is the same. Oh, well, yeah. Yeah, so it should be 0, 0, 1. Anyway, so we multiply these two matrices together and we get some solution. Looks great. But the wonderful thing about PyTorch is that you could do this with PyTorch. It's very simple to get the inverse of a matrix. This is actually the same syntax that you would get for. This is the same syntax as NumPy. So same idea. You define the coefficient matrix A, and one thing is, remember, I've done this so many times by now. One thing, by the way, is that if you don't actually write D-type float, this will define a tensor of integers, and then when you try to do some calculations, it'll throw an error. So if you're getting an error and you can't understand why, definitely put in the D-type float. That might come in handy for your homework too. That's been a common error with homework too, at least among the TAs. So we define the coefficient matrix. We define B. And we simply take the inverse of A, and we matrix multiply the two together to get the final results, to get X, which is 6, 15, negative 23, which is the same as here. Okay? Okay. Hey. Yeah, okay. All right. So that's wonderful, but one of the nice things about using PyTorch, as usual, is that there's a function for it. So with Torch, you could use the function lin. There's a linear algebra there's a functions in the linear algebra module, and you could use linear algebra solve. So you could do the whole thing with literally one line of code. You simply say torch that linear algebra that solve. You give it the coefficient matrix. You give it the sum. You give it the sum B matrix. And you just ask it to solve, and it will solve the system of linear equations for you. Make sense? This doesn't seem like a huge speed up, right? I mean, how much effort could it have been really just to write A dot inverse times B, right? Why does this exist? Yeah, please.
Actually, again, it's like an optimization thing where, like,
Yeah.
the right thing, you have to do, like, two operations at a time. But linear solve could have, like, some sort of method to kind of do it in, like, a try. So, like, maybe it has, like, an engine to it.
Yeah, yeah. It's pretty much exactly just an optimization thing. Again, so there are faster ways to solve. Well, there are a couple of reasons, but it's mostly performance. But I'm going to list all the reasons. So a big one people will say is numerical stability, which is actually a valid point. That certain methods aren't numerically stable, especially when finding the inverse matrix. So there is a sense where linear algebra that solve uses methods that are more numerically stable, especially like LU decomposition, things like that. And also, the big thing is, again, the performance. I think using efficient methods, again, LU decomposition, it makes a big difference. And in order to show that, we could write a little test code. Again, we have a little test code here where we have a coefficient matrix of some random variables. Yeah, coefficient matrix, n by n, 1,000 by 1,000 coefficient matrix. We have some solutions to the system of numerical equations. We make sure A is invertible by multiplying it by its transpose and adding some values to the diagonal, and by adding a large scalar. And then we simply test, and then I'm simply doing the start time of linear algebra solve and doing testing the time it takes to get the inverse, and then doing the inverse times B. And in effect, what we get is approximately a 25% reduction in speed. That's been fairly consistent regardless of the value of n I've chosen I made like n stupid big last night at home, and it's still roughly around 25% speed reduction. So it won't give you an order of magnitude speed up, but it will give you something, right? Does that make sense? Yeah, please. Yeah.
Is the lineage that solves that ecemjr type flow?
Oh, good question. Is the lineage that solve always a type flow? Yes, I think so. That's the only way it works for me. It threw an error where when I tried to give it an integer. So I think it always takes in a float. It's also possible, yeah. I would assume that I'm actually kind of surprised that a lot of these torch functions don't just cast the matrix as a different data type. Like that's what I would assume most of these functions would do. I mean, given that torch does Python tries to do everything else for you, I'm surprised it doesn't just try to cast your memory as a particular type for you, but it doesn't. So it doesn't like messing with the data type of the tensor, which I could understand. But if you don't want to, if you have that rule, it's a weird line to draw, right? I won't mess with the data type of your tensor, but I will broadcast it to all sorts of different dimensions. That's just a weird sort of philosophical line. Anyway, that's my rant. Okay, so systems of linear equations. I don't think so. One thing, so usually I had I was debating between going over sort of LU decomposition and eigenvalue decomposition, methods to solve linear equations, but also I don't want to go into them too deeply right now because I don't think they will be used in the near future. And I want to make this class a little tight as possible. I don't want to add in too much superfluous information, right? That's kind of the point of a course. You guys aren't coming here for me to breathe knowledge into you. You guys have the internet. You're coming here so I could sort of edit the knowledge down into a more easily digestible format, right? So we're going to leave the linear algebra solvers, and I think a better use of our time before the weekend will be to begin matrix calculus, and then once I give you guys a taste of matrix calculus, you could go home, chew on it for a while, and then next week when we discuss autoregression, autodifferentiation, then we could go into a lot more matrix calculus, right? But it's good to have it's good to dip our toes into the water first. So that's what we're going to do. We're going to discuss matrix calculus and just the introduction to matrix calculus, okay? And then the more advanced stuff we're going to discuss next week with autodifferentiation, with backpropagation. Okay, so derivatives, they've returned. So last week we discussed derivatives and how to take the derivation of a function with one variable. Remember, that was a whole thing. Even last lecture, we did that with the composite function, with the x to y function. What was the sine of log of x squared plus 1? But in our deep nets, most of the functions will have multiple variables. So we need to figure out how to take the derivative of activation functions when they have multiple variables, right? So for example, let's assume that we have the function ax is equal to xy. What is the derivation of a? It depends on well, the derivative is simply the idea of a derivative is how much will the value of the output change if we change one of the inputs, right? So if we have a function that has two inputs, then the derivative depends on if we're changing x or y, okay? So for this, we have to go from simple derivatives and we have to go into working with partial derivatives. And how do we represent large networks of partial derivatives, okay? So for instance, we have a slightly more complex equation, f of xy is equal to 3x squared y. And then, if we have this function, then we know the derivative, the partial derivative of this function is simply the partial derivative with respect to each of these variables. And if we organize it as a vector, we could say that we could organize this, we could organize nabla as a vector where the row represents the partial derivative of a function, and the column represents what variable you're taking the derivative with respect to. So in this case, we have one row, one function, and we have two columns. We have two variables we need to take the derivative with respect to. And so we could organizing it like thus. We get that the partial derivative of f of x is equal to 6xy comma 3x squared. Okay, it is simply equal to the vector containing the partial derivative with respect to the first variable and the partial derivative with respect to the second variable. Okay, makes sense? We're just organizing data. Okay, we could do this by hand. We could have written down this line by line. D of f of dx and is equal to 6xy. D of f of xy dy is equal to 3x squared. All that is fine, but we're just trying to compress the amount of information we have in a more digestible format. So we're just putting it together in a vector. Okay? So we could do this for other functions too, right? We could define another function, g of xy is equal to 2x plus y to the 8th. And so the derivative of g of xy is simply equal to the vector where the first element is d of g with respect to x, and the second element is d of g with respect to y. And in this case, the derivative is very simple to see. It's simply the vector containing 2 comma 8y to the 7th. Okay? So what do we do next? Well, we have two functions. So what do we do with the system of linear equations? When we have systems of equations, you just stack them on top of each other, right? That's all we're doing right here. So we have two equations where the partial derivatives form a vector. So we could stack those vectors on top of each other and get a matrix. So in essence, this matrix is simply the derivative of x stacked on top of the derivative of g. It is a matrix where we're taking the derivative of every function and then expanding it out. We're saying that the row represents the numerator of the derivative, where we're taking the derivative of some function. So row 0 represents the derivative of f. Row 1 represents the derivative of g. And the columns represent the variable that the derivative is taken with respect to. Okay? So column 0, we're taking the derivative with respect to x. Column 1, we're taking the derivative with respect to y. Okay? And combining these all together, we get a matrix that represents the partial derivative of all these functions, of this system of equations. Okay? And this is called the Jacobian matrix. This is literally what a Jacobian matrix is. All of you have seen Jacobian matrices before, right? This is a well-known physics thing. So, I mean, not a physics thing. This is a math thing, but it's used in physics a lot. So this is how we get to a Jacobian matrix. All we're doing with a Jacobian matrix is representing the derivative of a system of equations. Okay. So, maybe I'll zoom out in a bit. So for a function, so the literal definition is that if we have a function, f of x, which takes in a vector of variables and produces a vector y, that is a bunch of real numbers, then the Jacobian matrix J is defined as the first order, and this is important, it's defined as the first order partial derivatives of each component of x with respect to each component of, of each component of f with respect to each component of x. Oof, that's hard to say. So, for instance, again, what we did, we have the system of equations. This is a column vector where we have all the system of equations that consists of n possible variables, that use n possible variables. And we have those n possible variables. So if we multiply that together, then we get the equations back again, right? So again, this is the coefficient matrix again, except now the coefficients are not only numbers, they could be more than numbers. They could be, any of the variables could appear in any of these spots. Okay? So the Jacobian matrix, no, there we go. The Jacobian matrix is an m by n matrix where we have m functions and n variables. Okay? And one important thing to note is that hopefully this is the layout you guys are used to, but, hopefully this is the layout that you guys are used to. But this layout is called the numerator layout. There is also an analog to this, which is the denominator layout, where each row represents a different variable that you take the derivative with respect to, and then each column represents a different function. It's basically this matrix transposed. So depending on the layout you're choosing, the derivatives of matrices, the derivatives of Jacobians of matrices, it does change some answers. Okay, so if you're ever getting an answer that isn't matching a solution online, and you're very sure you're doing something correctly, then I would check what layout, if they're using the numerator or denominator layout, because people switch between these two a lot, and it's kind of annoying. But it's life. So, okay, so PyTorch allows us to calculate the Jacobian matrix as well. So let's go back to our system of equations again, and just rewrite some variables. Instead of xy, we're just going to write x0, x1. And we're just going to rewrite the equations. Instead of 3x squared y, we're going to rewrite it as 3x0 squared x1. And similarly, we do the same thing for g, where we define g instead of g, we write it as f1. And we say f1 is equal to 2x0 x1 to 8. Okay? So we say the Jacobian for this matrix, we know the Jacobian for this matrix is f0 on top of f1, which is d of f0 with respect to d of x0 plus d of f0 with respect to x1 plus d of f1 with respect to x0 plus d of f1 with respect to x1. And we know the analytic solution to this is 6x0 x1, 3x0 squared, 2, 8x1 to the 7th. Okay? So one sort of issue is that Torch doesn't actually give us the symbolic Jacobian, which is kind of sucks. If you want the symbolic solution to a system of equations, pretty much Mathematica is your safe bet. I would say use SymPy, but SymPy is unstable. So if you wanted the symbolic solution to this system, pretty much you'll have to learn Mathematica, which isn't too bad, but no, not necessarily. But we do. But the good news is that we don't always need an analytic solution to this, right? We don't always need an analytic solution. And in fact, when we're doing our auto differentiation next week, we'll only want the Jacobian, the value of the Jacobian for a particular input. So let's just in this case assume that the input x0, x1 is 1, 1, and we get a Jacobian that is equal to 6, 3, 2, 8. Okay? So that's what we know analytically. Okay? So the point of all of this is that I wanted to show you guys that you could do this. No. Okay, we'll just zoom in a bit. There we go. Okay, or we'll zoom out. Okay. We could do this with PyTorch. Literally what's required, though, is that we have to format, and actually, we don't need these functions anymore. These were just helper functions. You have to format the actual function correctly. And in this case, I simply said that if we get the function f, remember we have a function where it's these two stacked on top of each other. The function f is simply equal to 3x0 squared times x1, comma 2x0 x1 today. Okay? All I'm doing is defining the function. I didn't take any derivative. That's the original function. Okay? So I define a torch tensor that represents x. Again, like before, like in the text, I'm just saying x is equal to 1, 1. And I simply use the torch.autograd.functional.Jacobian function. I give it the actual function's f. I give it x. And it gives us a tensor of the Jacobian at a particular, at x0, x1 is equal to 1, 1. Make sense? Okay, so that's how you do it simply, and this is how you do it with PyTorch, okay? So the most important thing is that you understand what's happening with both. Understand how you're doing it by hand, and then how you can do it with PyTorch, okay? Just because PyTorch could do everything for you doesn't mean you get out of understanding what exactly is going on. Intuition is important because that's how you'll catch errors. Does that make sense to everyone? Okay. Okay. So you could calculate the partial derivative of any system of equations fairly easily using the Jacobian, and the Jacobian will make its reappearance next week when we discuss autoregression. And then finally, I just wanted to end the lecture maybe on some brain teasers, just thinking of some important derivatives, seeing if we understand what's going in some of these things. And two important derivatives. Let's say we have a particular matrix A. Oh, let's say we want to take the derivative of a matrix, a coefficient matrix that is A times x with respect to x. Okay? We want to take so this is literally what we were doing, for instance, in the system of linear equations. We were multiplying these two things together. We have a coefficient matrix and we have x. And now we just want to take the derivative of that multiplication. So the result of that derivative is equal to a. Now, why is that? Well, intuitively, it makes sort of sense. If we take any variable, a coefficient of any variable, let's say 2x, and if we have the function 2x and we take it with respect to x, then the derivative of that is 2, right? So it makes sense. Functionally, it makes sense. It follows sort of natural, what we know of mathematics naturally. But a way to think about this is simply the product of AX is a linear transformation, and each entry in the resulting vector is a linear combination of the components of x. So what we're doing when we multiply AX together for a particular, when we multiply AX together, is that the resulting value, the ith value of this vector, when we multiply AX together, we get a vector. And so for each element of this vector, I, what is that equal to? It's equal to the row of the coefficient vector times x, right? The sum of these things. So we know that this is, we know that this is what we're doing, right? This is physically the calculation, okay? So the derivative, so to compute the derivative in this case, why is this going? Oh. So to compute the derivative, we just compute the derivative of this with respect to x. All we're doing is trying to figure out for each position in the matrix in a new matrix for each position, if we vary x1 by a certain amount, how will that change xy? Okay. And to do that, it's not. Oh, I'm going to delete this part. Yeah, that was from an earlier thing. So to do that, we simply take the derivative of this function. And so if we take the derivative of each element xj of this, then logically it makes sense that the change in a particular value of x with respect to x of j is equal to that value in the original coefficient matrix. Okay. And the major thing is that if we're assuming denominator format, we would flip the indices. And that is simply because if you work out the actual matrix, the reason, if you use a different format, it would make sense. We would flip the indices, and the result would be x of at. Actually, I don't remember why. Okay, I'm going to fix this writing in a bit. That's not my best work. Okay. The other important derivative I wanted to go over is that if you're transposing a vector with itself, there we go. A much simpler derivative. If you're taking the multiplication of a vector with its own, if a vector transpose it with itself, then the derivative of this whole thing is simply equal to 2x. And why is that? It's simply because x transpose x is simply equal to a scalar value that is the sum of x0 squared plus x1 squared plus x2 squared, et cetera, et cetera. So we want to measure the derivative. When we take the derivative of that whole thing, we want to measure the effect each xy value has on the end sum. Okay? Every time we change x0 a little bit, we want to measure the effect it has on this whole sum. Okay? And in order to measure that effect, and the effect in this case is simple. If we take the derivative with respect to x0, then we simply, all these values disappear, and we're simply left with 2x0. So we're left with 2x0. If we take the derivative with respect to x1, all the other values except x1 squared disappeared, and we take the derivative of x1 squared, which is 2x1. So the derivative of z of x, these variables, is simply 2xn. And so the result of this is simply 2x of the original vector. Okay? And even that makes sense, right? We're taking x squared, we're multiplying it by itself. Right? So effectively, we're taking x, we're multiplying it by itself, we're effectively getting x squared. So the derivative of x squared is still equal to 2x. Right? So it makes intuitive sense. Right? So with the matrix derivative, we're still trying to keep the rules of calculus consistent, right? That's the most important thing. We want to keep these derivative rules consistent. But just the intuition, it requires a little bit of time to build up the intuition. So we're going to go over some more derivatives next week. But for now, I just wanted to introduce it. And introduce matrix calculus in preparation for the lectures next week. But otherwise, have a good weekend. Homework is due Monday. And the next week is on auto differentiation, where we'll use a lot of matrix calculus. So we're going to go over it more. So don't worry if you don't completely get it today. All right. Thanks, guys.
So can I kind of just scratch this part out?
Yeah, that was for